Okay. Can you see my screen now?
Yes.
Perfect. And then I think that when you are ready, Alej, I think that you can start.
Yeah, I am ready, so let's start. Good afternoon, everybody. My name is Alej, and I am a board member of WIA-E Barcelona. Welcome to the very first Women for Space conference of this 2021-22 season. And many thanks to our speaker of today, Dr. Ariadna Farrés, for making it possible. Before starting, I would like to present you the different events that we have prepared in this upcoming year. We will have 3 types of events. For one, Women for Space is a cycle of conferences in which women working in the aerospace sector will talk about their jobs and their professional careers. Space for Change is another cycle of conferences in which either space companies or associations will explain us their projects and how they influence the society. Aerospace, on the other hand, is a cycle of interactive workshops in which we will get involved in practical activities. This year, moreover, we will offer for the first time a service of mentoring. This service will be for young students who are interested in developing their professional careers in the aerospace sector. Next slide, please, Monica. As I already said, today we are having a Women for Space conference. And then on the 7th of October, we will have a Space for Change talk with Cosmic Research, which is a group of students from the Polytechnic University of Catalonia who develop rockets and conduct CANSAT competitions. Just next, on the 8th and the 9th of October, we will start our mentoring service with EuroAvia. In November, we will have our first workshop, which will be about the design and development of smoked satellites. In December, we will have yet another Women for Space conference with Sara Correllero. We are still working on organizing more and more events, especially for November and December, and for the rest of the course. You can follow us on our social media, Instagram and Facebook, or subscribe to our newsletter to be up to date with all our events. Without further delay, I would like to introduce you our speaker of today, Dr. Ariadna Farrés. She has a PhD in applied mathematics from the University of Barcelona and has specialized in astrodynamics and celestial mechanics. Currently, she is working with the Flight Dynamics group at NASA's Goddard Space Flight Center as an expert on the impact of solar radiation pressure on orbits around Lagrange points. More specifically, she has worked lately on 2 missions that in the next few years will be very important and will have a big impact: the James Webb Space Telescope and the Nancy Grace Roman Space Telescope missions. Today, she will talk about the benefits of using solar sails on space missions to the Lagrange points instead of using the more classical chemical propulsion. She will also explain us how the necessary trajectories and maneuvers are computed. If you have any questions, you can write them in the chat during the presentation, and we will manage them after Ariadna's talk. Thank you, and enjoy the presentations. As I said earlier, many thanks, Ariadna, for being with us today. And now, the floor is all yours.
Hello. Can you hear me properly?
Yes, we can hear you. Yeah.
Okay, I can share my screen, right? Share entire. Okay. And slide mode. You can see the slides now, right?
Yes.
Yes.
Okay, perfect. Okay, so, whoops. Okay, so well, first of all, thank you for the invitation. It's a great honor to be here talking to everyone. I always start presenting myself, but you did a very good job, so I think I don't need to go over this slide. So essentially, my idea for today, when I was asked to give a talk, was, well, maybe why not talk again about solar sails? That it's what I studied during my PhD, and actually it's kind of what brought me to NASA, right? So I was planning to try and explain a little bit what are solar sails for those that have not heard about them or don't know a little bit, have heard the name, but really don't understand where the concept comes from. My main research was on doing solar sails around Lagrange points. So I'll try to explain what Lagrange points are and what are their interests for mission applications. That are a lot of mission applications that are now running around Lagrange points, and then a little bit of control strategies and so on. My background is mathematical, and I'll try not to make a very technical talk, but I just want you to get a general idea of the tools and how things move in space and how we use math to kind of develop trajectories and control strategies. Okay, so what are solar sails? So solar sails are essentially a new way of propulsion system that takes advantage of solar radiation pressure. And essentially it's just the sunlight just impacts the surface of your satellite and bounces out. And this kind of adds an extra acceleration to your spacecraft. This was seen back in the 60s when they were doing orbit determination. So they were trying to track several spacecrafts around the Earth, and they were finding some misalignment between the tracking data and what they were expecting. And when they added solar radiation pressure, they managed to find a better fit. So the idea comes from, why not try and use that to navigate? So thinking about the sunlight as wind on space and try and use that to kind of move around space. And if you want to really take advantage of that, you need a very large sail, so a very large reflecting area, so that you can capture as much photons as you can, and you want it to be very light, very thin, and very reflective. And the idea is that if you manage to do that, you have an unlimited source of propellant, because the sun is not going to stop emitting light. So you can do long missions, applications, and things like that. So the general idea is essentially, what is solar radiation pressure? You have, like, imagine a flat surface, and when your photon just reaches your surface and bounces back, there's three effects that take place. One is the absorption, which is this one here, and I messed up the equation, sorry. The first one is the absorption, and essentially it's like a solar panel. Your area just absorbs everything on the light. So the force from the sunlight just comes here, is absorbed, and produces a force along the same sunline. When you have something that is highly reflective, what you do is you have that it just bounces up and down, and you get a net force on the normal direction. And then you might have some diffusive reflection, it's just that the light that bounces scatters all around, and you get a small thrust in a different direction. And this sum of the three will depend a lot on your reflective materials and the reflective properties of the different of your spacecraft. With solar sails, we essentially want to have something that is super reflective, so there's almost no absorption and almost no diffusion, and everything is just reflective. So in the ideal case, and this is the ones that we start for modeling, is we assume that our solar sail is flat and perfectly reflecting. So our acceleration is given by this equation here. And just notice it's proportional to the area. So the larger the area, the larger the force or acceleration that we'll have. This constant here is essentially measuring the amount of photons that you reach depending on where you are. And if the closer you are from the sun, the larger this value is, and the further away you are from the sun, the smaller. And then this term here is essentially telling you it's the reflective area. If you have your sail that is completely perpendicular to the sunline, you're getting all the sunlights are getting bounced and reflected, and you have your maximum acceleration. If you tilt this with respect to the sunline, like in this plot here, you have this one that is reflecting. The amount of area that is capturing photons is slightly reduced. So essentially, you get max acceleration when you have completely perpendicular solar sail, but you can control the thrust direction when you change the sail orientation. So you kind of have to play with the two. And this other part here is just another way to write these equations, and is we can write this similar to what is the gravitational pull of the sun. If we are familiar, like this G times ms divided by distance squared is the gravity of the sun, and we can write the acceleration of the sail in terms of a multiple of the acceleration of the sun, because essentially they're in opposite direction, right? And this parameter here, beta, is essentially measuring as it's called the sail lightness number. It just measures how effective our sail is. The larger this number, the larger the acceleration of the sail. Okay, and there's other two main parameters that we usually take into account. That it's the two angles defining the sail orientation. The sail orientation is given by the normal vector of the sail, and essentially, depending on the orientation that we have to these two angles, you have more or less. And just mention that solar sails cannot be pointing towards the sun, or the normal vector cannot be pointing towards the sun. So essentially, we always get thrust or acceleration in an opposite direction of the sun line. We can never point towards the sun. So the angles are limited to plus or minus 90 degrees with respect to the sun line. So I always like to make these analogies, like we like to compare solar sailing with wind sailing or sailing in the sea, right? And I remember when I was first studying this, that people asked me like, okay, but like, can you go towards the sun? If the solar radiation pressure is just pulling you away, it's coming from the sun and it just pushes you away, can you go towards the sun with a solar sail? And the answer is yes, in the same way that with a boat, let's say you can go towards the wind, right? You cannot go directly in straight line towards the wind, but you can do zigzags to get there, right? And the fact that even if the wind is pushing here, you can do zigzags is because there's some kind of drag, and in this case, it's water that is doing the drag. In the case of solar sails, there's no drag in space, but we can kind of force this drag. And essentially, if you have a solar sail in here, and you have the acceleration, like the sunlight is pushing you here, and the normal direction is aligned or in the same direction as your velocity vector, you're adding acceleration to the velocity. So you're kind of adding energy to your spacecraft, and it will start spiraling outwards, and you'll get things that escape from the sun, right? So if you want to go from the Earth to Mars, for instance, you'll have to point your sail in this direction. And if you want to go towards the sun, the idea is to use the sail to kind of slow you down. So if you have that your thrust vector or your acceleration vector from the sail is pointing not in your velocity direction, but away from the velocity direction, you're kind of generating a small drag. You're slowing down, so you're using the acceleration to slow you down, and you'll start spiraling inwards. This is just to show that despite the limitations on the thrust direction of a solar sail, you can do a lot of maneuvers, and you can be agile in terms of going inside the sun, away from the sun, and visit other planets, and so on and so forth. So what are the type, like if you want to use solar sails, it's interesting to see like, okay, what type of missions can I do that I cannot do with another spacecraft, right? Because that will a part of being a very nice and cool way to traveling around space. If we want people to invest, we need to show that it's useful for something. And like the main one that many people do is like quick escape from the solar system. I'm sure you've seen papers on trying to visit Proxima B or Proxima A, I never remember which one is, but like other planetary systems or so on with a solar sail. We might get faster than with other, because the idea would be that as we're escaping the solar system, we're constantly accelerating our spacecraft. So essentially, you could just go close to the sun to get a big boost, and then just quickly escape from the solar system. Other interesting missions are multiple rendezvous to asteroids. One of the problems when you want to go and visit asteroids is that you have a limited amount of thrust, and once you visit a couple, then if you want to go and see another one, if you have not had that into account when you are planning your mission, you sometimes don't have enough fuel for that. In here, because we have a limited fuel, you could kind of use a solar sail to go and visit different asteroids as your mission evolves. And And also you can be more flexible in terms of which asteroids you go to see if they change your launch date, right? Then other interesting is just using the solar sail to kind of deviate the classical Keplerian orbits and libration point orbits. As we will see later on, adding the solar sail essentially allows you to generate a new set of family of natural trajectories in space that are not achievable with regular propulsion systems. One option will be just to use solar sail to change the inclination of the orbit, right? And go from a planar to a completely polar orbit. And there's a lot of others. Another final is just using solar sails to deorbit. It's using them for the opposite of what you would use, but you can use a solar sail to add a lot of drag. And when it comes to space debris and so on, there's many people that have thought on using solar sails to add extra drag on your probe and just fast re-enter the atmosphere faster than without a solar sail. Okay. Ooh, this doesn't change, damn it. Okay. Yeah, and just to show that it's not just a fantasy, there have been solar sail missions. They all are tech demo, but essentially in 2010 was the first time solar sail was deployed. That was by JAXA in 2010. They just wanted to test that they could deploy and prove that they could measure the acceleration by slightly changing the orientation you would find, so that the force models match the actual real model. Then in 2010, NASA deployed nanosail, and here is just an idea, reference on how big the solar sails are relative to people. And in the past, sorry, this is 2015, I have a typo, but in LightSail 1 and LightSail 2 were deployed in 2015 and 2019 by the Planetary Society, which is probably the most active enterprise or group of people working on solar sails. In 2021, NASA should launch the solar sail NeoScout, and in 2026, at the best of my knowledge, JAXA will also launch another solar sail. This one will visit an asteroid, and this one is going to visit asteroids in the Trojan asteroids. So we're hoping to see more solar sails in the near future, and not being just tech demo, but actually doing real mission applications. But for this, we need to prove that solar sails can do very interesting things. And this is one of the points of trying to study how solar sails impact the motion around Lagrange points. And I just wanted to start introducing what Lagrange points are. As you might know, when you're trying to do trying to model the dynamics or the motion of a spacecraft around space, you need your force model. So you have that your acceleration vector is the sum of all the gravitational planets that you want to put here, and here we'll add our solar radiation pressure. This set of equations is always super hard to study and understand, and that's why we usually tend to simplify as much as possible our equations of motion so that we can kind of study the underlying dynamics that happens. So one of the classical models to study is the restricted two-body problem. And if you're not familiar, essentially what we have is, like, imagine the sun and the earth, and you have your spacecraft, and we have the sun and the earth are interacting, are orbiting around their center of mass in a circular way, and they do not affect each other, but they do affect gravitational, gravity affects our probe, that will be our solar sail. So you'll have our spacecraft is affected by the gravity of the sun and the gravity of the earth, and we also have this extra term here of the solar sail. We write down these equations in an inertial reference frame, so we're rotating reference frame, sorry. So we have that the sun and the earth are always rotating. The line that joins the two bodies is fixed along the x line. So essentially, they are fixed, and what's rotating is the reference frame, right? And what we have, the equations of motion are the ones that are written here, and we have to add this acceleration extra term. Without the acceleration extra term, this problem has been studied long throughout the years, and there's a lot of interesting results that show a lot of interesting orbits, periodic orbits that exist in this system, which I will not go through all of them, but some of them. One of the most relevant things are the Lagrange points that maybe some of you have already heard about. And essentially, this system has 5 equilibrium points. It's 5 places where all the forces that enter here are counterbalanced. So essentially, one is easy to imagine. If you have the sun and the Earth that are pulling, are attracting our spacecraft, there's a point in between where the acceleration from the pull from the sun and the pull from the Earth cancel out, and you have this L1 equilibrium point. So essentially, you would have a point where you're orbiting around the sun at the same rate as the Earth. Okay, another one is L2, and it is true that I just said the gravity, but there's also the centrifugal force because of my rotating reference frame. And if all these 3 things cancel out, I have this L2 point here. You also have L4 and L5 that form an equilateral triangle here, and then there's L3 on the other side of here. It would be like an anti-Earth. All of these points have a lot of interest, but for mission applications, the ones that we've recently been visiting them more are L1 and L2. Gaia and I think the James Webb Space Telescope and Roman Space Telescope will be launching here in L2 because it's a very interesting place to kind of observe the universe. And then missions like SOHO, ACE, Discover, they are around L1, and this point here is very interesting for sun observations. And when it comes to the dynamics, L1 and L2 are points that are linearly unstable, and that means that trajectories tend to escape around L1 and L2. I just wanted to show this very quickly. Essentially, it's like apart from just the L1 and L2, there's a huge variety of different periodic and quasi-periodic orbits around here. Those are natural orbits that exist. They are the known like halo orbits. So essentially, you have an orbit that if you have the Sun-Earth line, it's just orbiting around a halo. So it's essentially just having the sun in between, and you just orbit around it. There's the Lissajous orbits. Those are names that maybe you've been hearing around, or if you Google them around, they exist. It's very nice, interesting, different families of periodic orbits that some of them are useful for mission applications. So the question is, what happens when you add the solar sail with this equilibrium point, right? Well, essentially, as I told you, like just think about L1. L1 is the point where the 2 forces cancel out, right? When I add the solar radiation pressure, I'm essentially adding an extra acceleration in the opposite point away the sun. So now if I add up these accelerations, I would tend to escape. This would not be an equilibrium point, but obviously it's just slightly displaced. There's another point closer to the sun where all these forces cancel out. So essentially just adding the solar radiation pressure, having your sail perpendicular to the sunline, just essentially just displaces your equilibria closer to the sun. So instead of having L1 here, the natural L1 of your system is something here. The larger the solar sail, the closer you'll get to Earth. If it's very small, you just displace. This size can be up to 1,000 kilometers. So it's quite a large displacement. And then if I just slightly tilt the orientation of the sail, I'm essentially adding another extra acceleration, but not in the same Sun-Earth line. I'm adding acceleration maybe above the ecliptic plane. That means that on the Sun-Earth line, I will not have an equilibrium point, but this one can be displaced above, right, or below. So depending on the sail orientation, I can artificially displace the location of the L1 point, and I can generate a family of different equilibrium points, one for each fixed orientation. Right. This is just a picture trying to show the location of this different equilibrium points depending on your sail lightless number, like between 0.01 and 0.02. You have kind of small circles around L1 and L2 of equilibrium points. The larger the values of beta appear, you start having larger, and they kind of merge into sort of tubes And I could explain a lot of here, but essentially I wanted to get the idea that I can artificially move those points and generate artificial equilibrium points on different locations in space. Right, and the same happens with the periodic orbits. What happens is that, again, if I slightly move the orientation of my sail, I can slightly displace the periodic orbits. The only caveat is that in some cases, moving the solar sail essentially breaks a little bit the area preserving property, so essentially adds some dissipation, and we can actually displace and find equilibrium points around everywhere, but we cannot find periodic orbits everywhere. They are almost periodic orbits, let's say. It's only in some particular sail configurations that I find the displaced periodic orbits. And these are just pictures of this sort of type of periodic orbits. So what can we do with this fact of displacing orbits, right? In terms of mission application, it opens a wide new range of opportunities. Like, for instance, a classical one was called Sunjammer, or was called in the past also Geostorm. And essentially we have these great corona mass ejections that are from time to time come to the Earth and can be hazardous for our satellite around here. So we have a spacecraft called ACE that is orbiting L1 and is kind of checking if a corona mass ejection is coming. And there's a warning time of 1 hour between ACE and the Earth. So once ACE sees the geomagnetic storm, 1 hour later, they arrive to Earth. The fact that with a solar sail, we could double the distance from L1 to the Earth, so put ourselves here, this would give us an extra hour. So just putting a solar sail here and just displacing it, we don't even have to be orbiting a halo orbit. We can just be 5 degrees off the sunline, and we can do that with a solar sail by just tilting the orientation. We can be there and just observe the corona mass ejections and give early warning of the geomagnetic storms. And another interesting is, as you know, to observe the poles of the Earth, we are obliged to, because of the laws of physics, we have to be orbiting around the Earth. Using a solar sail, we could kind of artificially displace L1 above the ecliptic plane, so that we have a constant monitoring of the ice caps in the North Pole, and the same, we can do the same for the South Pole. The only thing is, like, to allow and have this, we have to have a relatively large solar sail, but there are other periodic orbits around here that can also be displaced and offer interesting opportunities. So using solar sails would enable us to have constant monitoring of our Earth poles, North and South poles, which might be interesting for climate change or things like that, to kind of constantly monitor those things. So these are kind of interesting mission applications. The main problem is that the points L1 and L2, it's not a problem, it's just that it's how it is, they are unstable. So that means that the trajectories naturally escape from L1, that we cannot, even if it's an equilibrium point, once we are there, after some days or years, we just naturally start to drift away from that point. So we need to constantly do small maneuvers to kind of come back to L1 and L2. So what I want to try and explain now is how we can use some ideas to try and perform. So how can we do those controls with a solar sail, and if it's possible to do controls with a solar sail, or if we would have to put an extra thrust just to come back, right? So let me just drink some water. Okay, so station keeping. And this might seem a little weird, the description that I'm making, but I hope everything kind of just gets the general idea. So station keeping is essentially this sort of maneuvers that you have to do to escape. We usually are used to look at things in position and velocities, but when we look at things around Lagrange points in position and velocities, it doesn't actually give us information of how we are escaping. We just know that we drift away. But we can use what is called the Floquet mode reference frame, or linear dynamics reference frame. There's this sort of particular division of my phase space in 3 planes that explains me very well how things are moving. And essentially, you can separate your 6D phase space in 3 different planes, one plane has this, what we call saddle, that essentially is showing me how I'm escaping. I have two escape trajectories, so I'm just naturally drifting around along this direction and this direction. And there's two intaking directions, that is this one is this one. This is what is called the invariant manifolds of my orbits. That it's two kind of natural trajectories that escape me, make me escape from my point, or just bring me back to my point. And then with the other two, we essentially just have rotation. So essentially we're rotating around the point and we're escaping. So we're kind of escaping in a spiral in one direction, and there's an inward direction that we just kind of come back in. Okay, so in general, when we don't have a solar sail, we just have a chemical propulsion system. Every time the same happens, either one, we're just escaping. And I like to compare how we do station keeping with trying to keep a ball at the summit of a mountain, right? In general, this is an unstable equilibrium point, right? Because we're here, but the moment we just move a little bit, the ball will fall down. It's not the same when we're on a valley. That is also an equilibrium point, but it will remain fixed. Like we can move the ball a little bit and it just comes back. When we're in the summit, it will either fall in one part or the other. And if we want to keep it here, every time it falls, we just have to push it back up, right? And we just do a maneuver and we just push it. If we are just pushing in, this would be kind of what we do with our thrusters. We're pushing the ball up, we're giving it a delta V, and it's going up. So we're essentially just pushing up and back. So essentially, if it falls on one way, we just push it one direction. If it falls on the other, we push it on the other. And every time we want to do a maneuver, we either go on one way or the other, and we start just pushing the ball up and down, right? So if we look at our trajectory in this fancy reference frame, what we see is that in position, we just are turning around here. This would be in the case of a halo orbit, right? But the same would happen if we're in a fixed point. We're here. And if we don't do anything, if we look things on our saddle and the center parts, we just start escaping along the unstable direction. We start rotating. At some point, we start doing weird things. And that's just because we're far away from the orbit, and this nice reference frame doesn't work anymore because it's a linear approximation of what's going on. But if we do a control, that is essentially every time I'm escaping, I just push it back in, I manage to control. And here you see that I'm not escaping. I don't have this teeny tiny tail that I was seeing here. But what happens in here, in this reference frame, is that here is the saddle. I start escaping. When I'm here that I'm too far, I just push my spacecraft here towards the stable, and I just escape again. I do another maneuver to push me here, and I do this. And I kind of are pushing all the way, and I'm staying controlled. And in the other ones, I have this kind of rotations and this weird motion here, but I'm just orbiting around. I'm not escaping around here, but we just need to essentially take care of things here on the saddle plane. That is the one that is just drifting me away. And this is interesting because it shows you how to understand station keeping maneuvers, right? And the question is, can I do the same with a solar sail? Like, I'll be drifting away, but how can I push? Like, the acceleration is very small, right? I cannot do a big maneuver. When I'm doing a delta V maneuver, I'm essentially just jumping on the phase space. With a solar sail, I cannot drastically jump because it is a small acceleration, right? But can we use similar ideas for that? Well, we can, again, just have our representation here, and we just let us think what happens when I change the sailor orientation, right? When I changed the sail orientation, what we saw before is that I was artificially displacing my equilibrium points, right? Every time I change the sail orientation, if I'm perpendicular to the sun, I have this P0, this is my fixed point. When I change the sail orientation, I move the equilibrium points, I don't know, 10 kilometers away or 100 kilometers away. But I was also moving all that stable and unstable manifolds associated with my points. So I'm essentially moving this saddle that I have here. When I move the sail orientation, I'm just moving the saddle here. And if originally I was escaping around this direction, when I change the sail orientation, if the sail orientation is around, if the new saddle is here, I'll just come back to close to P0. If my new sail orientation is here in the green part, I'll just start escaping again. So if I manage to move the sail orientation in a way that I just drift the saddle far away, I'll just start going back to my P0. And then when I come back, I'll just restore the sail orientation, and I'll be doing that. In a way, you can think that I'm kind of playing ping pong with two different saddles, right? Every time I'll just be moving my sail orientation, and I'm just escaping, and then I come back, I escape, and I come back, and my trajectory is being bounced back and forth by two saddles with two different sail orientations. On the center parts, you just start doing orbital motions around the different. So it's just a concatenation of rotations around these points. So essentially, if we go back to the analogy of the mountain, which I'm not sure if it's the best example in this case, but essentially, when I'm falling down and my ball starts falling, I cannot push the ball. But what essentially I'm doing with what I'm saying of moving my saddle is that I'm essentially moving the mountain. I move the mountain so that now the slope just brings me back to that one. And if it escapes on the other way, I just move the mountain so to go back. And by moving the mountain, I'm in solar sail space phase, I'm just moving the equilibrium points so that they kind of naturally drift things along. So the main difference between impulsive and low thrust is that when I have impulsive maneuvers, I'm essentially jumping in the phase space, right? And I do the same. I want to cancel that, so I just jump in the direction that just brings me close to the stable manifold. When I'm using solar sails, I change the phase space so that the new phase space brings my trajectory close to the original saddle, new stable manifold. Okay, so this is the main difference. So essentially, this is just algorithmic expression of my station keeping strategy. Is like, okay, if I start with this set of angles, I start the escape. When I'm far away, what I consider far away will depend on my mission constraints. I choose my new sail orientation that brings me back. And if I'm close, I just restore again alpha 0 and so on, and I bounce one for that. The key point here is how do I choose this new sail orientation? And this is the tricky part. I won't get into much of the details, but essentially, this is the key point to see how to go back. This is just very quickly, but essentially you can write down the expressions of where my fixed point is and where I want my fixed point to be. And I just need to solve this to say, okay, this is where ideally I want to be, and what are the angles that give you back here. Just need to solve this type of systems. I won't get into the details, but this will be the general idea. And are we able to do control always? Well, not always. It will depend. Essentially, I want, because I'm escaping here, I want my new set of fixed points to be around here, because if I'm here, I can just essentially go back. But imagine that when I change one of the sails, I just experience changes on the equilibrium point along this line here, along the stable. If I'm not able to find equilibrium points in this side, I will not be able to control my orbit. So I need to be sure that when I change the sail, I'm able to move the spacecraft in this direction here. This is just some examples of that we can apply this, and the same way that I was showing before for a classical thrust here, you see the difference. You are escaping around here, and instead of just directly jumping here, as we were seeing on the previous example, when you use a solar sail, you drift on another saddle. The saddle is around here, the new saddle, and once I'm here, I just escape again and I go. And on the centers, you just spiral around, and on the XY, you just see a squiggly motion here, but I'm just staying close to my equilibrium point. And this is the set of sail orientation changes. It is very small because it's less than 0.2 degrees that you need to change. That is very linked on how far you're allowing your spacecraft to move. The further away you allow it to move, the more you can impose the changes in here on the angles. So just playing with some of the parameters, you could have larger sail orientation changes of 2 or 3 degrees, or only half a degree, and so on and so forth. So essentially, with the talk, I just wanted to show different what are solar sails, just to see that they enable very nice and challenging mission applications. From a mathematical point of view, that is where I come from. Solar sails also open very nice and interesting mathematical problems, like how adding a solar sail changes the phase space, changes the natural behavior of a system that we've studied for years, and then that the maneuver planning of solar sails or any low thrust propulsion system is completely different with chemical propulsions. The cost functions are different. We don't have in solar sails a propellant. We do not have to minimize the amount of fuel we have. We can minimize the time it takes us to go from point A or point B, but we don't have that constraint, or we can have some constraints on how fast we can move the solar sail. But the cost function that you'll pose is completely different than when you use classical chemical propulsion systems. And essentially, that's all I have. I hope you got a general view of solar sails. And if you have any questions, just feel free to ask.
Yeah,
okay.
Thank you. Yeah, Ariadna,
That's all.
a lot for your speech. It was really nice. And really, I think that you got your objective, because for me until now, I could say that the Lagrange was just a mathematical equation, and now, yeah, it's really more interesting. I mean, I want to learn more even, and I understood some stuff. When in the beginning I was thinking maybe I will be lost, but no, I could follow some of them.
Okay,
and
that's good.
Yeah, really interesting. And thanks, really. Yeah, it was really
okay,
nice.
Cool.
And we have some questions in the audience. So the first one was from Artemis Westenberg, and the question was, what does quickly escape or solar system mean? Within a year or within 10 years?
I think within 10 years, maybe 9. I think you can decrease slightly the time it takes for New Horizons that escaped. I think it took him 10 years. With a solar sail, you could go with 5 years or something like that. It does depend on how large your solar sail is. I have seen papers that depending on the material you put, you kind of add an extra booster with that. So it really depends a lot on the solar sail. But yeah, I think it's between 5 and 8 years would be how fast you could escape, from my understanding.
Okay. Thank you. Another question for Eduardo Monroy. I said, are there no natural objects at the equilibrium points?
Are there? So around L1 and L2 and L3, no, just because they have this natural drift that they escape. L4 and L5, they're linearly stable. And around in the Sun-Earth problem, I think there's nothing, or we haven't discovered anything. If you just change and you put the same, the Sun, but you change it with Jupiter, around L4 and L5 is where you find the Trojan asteroids. So they're naturally captured over there. So there are naturally captured things in other rest-frequency body problems. In the Sun, Earth, I think there's some people that think there might be an asteroid captured around one of them, but it has not been proved from my end, from what I know.
Okay, okay. And the last one is from Ana Ruiz, and it said, how do you think the development of this technology can help us on Earth now or in the future?
Can help us on what?
How do you think the development of this technology can help us on Earth? On the
on Earth. Okay.
Yeah.
Okay.
And now or in the future? Or?
That's a good question. I think it helps in some of the missions. If you want to have observations of different parts of the Earth, it does help on that. I don't know if that's a direct way to help on Earth. It just helps other type of propulsion system. It can help on deorbiting things. We have a big problem with space debris. There's a lot of objects in low Earth orbit. So if we manage to bring them back to Earth, that can help. And also just to have different type of mission applications, let's say. I don't know if that's a good answer.
Yeah. Yeah. And then I have more. Well, another question is not from the audience.
Yeah.
But, for example, which message do you want to transmit to the new generations?
Okay, yeah, I've been thinking of that. It's always hard to what to say. I don't know. I would say that at least in the aerospace field, hey, don't be afraid to move around and change career paths. Every change you make brings you to another interesting project. I think we used to live in a world where you would just study something and end up working on that thing, and that was your life. this doesn't work like this anymore. So just don't be afraid to explore different countries, different places, and even if you think that your profile doesn't fit exactly that job description, just go for it. You never know what will happen. So that would be my advice.
Thank you. And maybe we have enough time for another one also. How you value the aerospace sector in both and negative on the impact and necessity?
I'm sorry, I couldn't completely understand that. Can you repeat?
Yeah, of course. How you value the aerospace sector and the impact of the society? See how you will
that
the aerospace projects can be impacting in our society maybe in the future, or if they have already an impact in our society, because
I think the aerospace has a lot of impact. I mean, just first from technological aspects, like right now we depend so much on space. All of our phones, GPS depend on satellite and things like that. So we are truly dependent on things on space, but also on the understanding of the universe, of things. We rely on satellite and so on to make observations and make science advance. So it has a lot of implications on everything. And I think we were talking before, like there's no just one thing, like don't narrow mind aerospace in just putting satellites on orbit. No, there's communications, there's astrophysics, there's even geology, biology, and things like that are included in the aerospace centers. I don't know. For me, the cool part is that it is so vast that you can always learn something interesting and be involved in one way or another.
I completely agree, because we also think on that. But do you think that the society really relies about all this way to think? Because I think that you know about that once you enter in the aerospace, and then you realize that it's like, oh yes, it's not only satellites, it's also this and mathematics and physics, and can be a lot of people involved. But I don't think that the society by himself, when you are young and you go to choose a degree, for example, you see the aerospace like maybe a difficult degree or something more orientated with the satellites. I think that you are not. You like you, for example, you started mathematics degree. So who will tell you that you will finish in the aerospace? No, so I think that
exactly.
That until that we found the aerospace world, no?
I agree. I mean, for me, I always loved aerospace. Like I always loved space, but I don't know. I also loved math, so I just started with maths because I don't know, something when I had to choose, I just chose maths, right? But it's true that I always have that, okay, how can I apply maths to space, the space industry and so on? I think whenever you start studying any other degree, if you like space, you might also be like, okay, how can I apply what I'm knowing to things in space? And I think things are going to change that. And that's just the gut feeling that 20 years ago, no one knew about satellites or things that were going on space. And you had the Apollo, the astronauts. Oh yeah, people went to the moon. But that's all we've done. And now, either because we also have all the space industry that is putting people in space, but also we have a lot of people that are aware of things. I think things are going to change. People are going to be more aware of how important it is and how relevant space, the space industry is.
I agree. Nice. Well, I think that we will leave it here. So if there is more questions, let me check.
I don't know.
Well, Eduardo Monroe is just saying thank you very much for your answer. And yes, I had here about Trojan asteroids.
Okay, cool.
Asteroids,
Yeah, perfect.
Good. Thank you, everyone, I think. And thanks for coming.
Thanks for the invitation.
The next one we'll have an ex-woman for space in the next month. And we are finishing to know exactly the date and the hours, but it's coming up. It's coming soon. And then we'll have also a space for change on October. That we said in the agenda. So I hope that all of you want to participate and see the next. Okay. Thank you, everyone. Bye.
Bye.